Okay, now we get into the nitty-gritty of why we have terrestrial planets, rocky planets, and Jovian gaseous planets. So one of the things we need to know or recognize is that at the time of our solar nebula, and actually yet today, if you look at our solar system as a whole, it's mostly hydrogen and helium. And look, 98% of what our nebula started out with was hydrogen and helium. And it honestly still is today because those atoms are conserved. There's a little more helium than there used to be. But anyway, so I'm also going to put up then the next abundant stuff that was in our nebula that formed the sun and the planets are these compounds. They are hydrogen containing compounds. Of course, water, H2O, is a hydrogen containing compound. The other two compounds listed are methane, carbon, CH4, and ammonia, NH3. Now, one of the things I want to kind of point out is that this column right here, okay, the temperature at which these things go from being a gas to being a liquid or maybe even a solid, the temperature at which they come out of being a gas anyway. Notice that hydrogen and helium, and it's kind of related to they're just so darn small, it's hard to get them to stick together, but they do not condense. They will not condense at a cold temperature. Notice that in order to get the water, methane, or ammonia to condense in our solar nebula at those pressures, it would have had to have been 150 Kelvin or colder. Then you could get that to condense. Okay, and the hydrogen-containing compounds are 1.4% of the stuff that we have to make our sun and the planets. And so if you're like me, you're like, looking around this room, I don't see a lot of hydrogen and helium just by themselves. And those other compounds, maybe a little bit. But that leaves two other components. So these are the four components that were most abundant or by most amount in our solar nebula that ultimately became our solar system. So the thing here is rocks and metals. The thing that's different about them, well, first off, notice that they aren't very abundant. You add the rocks and the metal together and you get 0.6%. Okay, that's not a whole lot. It's kind of rare. But the other thing, notice that the temperature at which they will go ahead and go from being a gas to condense to being a liquid or solid, notice that you can have toasty temperatures up to 1300 Kelvin or 1600 Kelvin to go ahead and get condensation to begin. So this is to say that kind of near the sun where it was toasty, those things could go ahead and condense. And I'm going to talk about something called a frost line. I'll go ahead and kind of draw it here. Okay, frost line is actually a temperature. Okay, and actually it had to be cold enough beyond the frost line to get those other, the water, the methane, and the ammonia to come out of its gas phase. Okay, so that's important to kind of distinguish why near the sun we didn't have to have it as cool to go ahead and get the rocks and metals to go ahead and condense. Then you had to get far enough away from the sun to go ahead and condense those the other. Let's see if this will work. Okay, let's see. I'm determined. Hang on, hold that thought. Let me turn this back into my arrow. Okay. So to kind of make that point, here's a little applet that, I don't know if you see that yellow up there, okay, and basically down here at the bottom, this is like right up next to the sun, and this is 1 AU from the sun, that would be where the Earth is, 2, 3, 4. So the way this works is I could click right here, about 1 AU from the sun, and here on the y-axis is temperature. So of course, as I get closer to the sun, what's going to happen? It's going to get hotter and hotter. Okay, if I get farther from the sun, okay, notice it's going to get cooler and cooler. The temperature is going to drop. Okay, high temperature up here, lower temperature, cooler temperature here. So to kind of show you some milestones with regard to temperatures and our sun, the green area, the sun to that green area, actually nothing's going to condense. And can you see that blue line out there? So from the green line to the blue line, you're going to go ahead and it's cool enough for rocks and metals to condense. Okay, and then beyond the blue line, it's cool enough for your hydrogen-containing compounds to condense. Okay, so that is important to why we got what we have. I'll go ahead and reveal this whole slide. Okay, so just to kind of point out what's going on here again, okay, and you'll see this in a couple different ways, but this is the sun. Okay, actually it's the proto-sun. It hasn't turned on yet, and I'll kind of show you why I know it hasn't turned on yet. It hasn't kind of cleared all the dust out of the plane of the ecliptic. So this right here, this white line right here is the frost line. So out here, you can actually, I don't know if you could tell it, but they're actually blue dots that are available to go ahead and, I kind of think of the planets basically kind of in their lane, kind of getting bigger and bigger and bigger, kind of like a snowball. We call that accretion. Okay, so out there's more stuff that can go ahead and accrete, make those larger planets because we have access to those compounds that contain hydrogen. Inside, smaller planets, because all you're going to get is the metals and the rocks. Okay, so you see the term planetesimal. I love the term planetesimal. Okay, so I kind of mentioned that it's like building a snowball, one big snowball in the lane, okay, early on before, as our solar system was forming, our planets were kind of coming together. But what happened was kind of we had multiple planetesimals that actually would kind of collide and become larger and larger. So I think this is a pretty good little animation. I need to turn it back into my arrow. Okay. Maybe. I give up. Okay. So it would have just kind of shown you that in that red region now, that's on the other side of the frost line. And again, you have access to now more particles that can kind of snowball up and become a planet. The gray area outside the green, that's where it was cool enough to go ahead and have rock and metals go ahead and make planets. So the process of making planets is called accretion. So kind of from left to right here, you see kind of a time where from left there was a bunch of like stuff, that kind of loose miscellaneous material that actually here in the middle figure, you can kind of see that we're kind of forming those planetesimals that can collide and make larger, ultimately, planets. Okay, so now the Jovian planets, like I said, were on the other side of the frost line, and so they had access to that extra material that inside the frost line they didn't. Notice, and actually I should say, when we start to study the gaseous planets here in this unit, we're going to see that they do have, gaseous hydrogen and helium, or even hydrogen and helium that is metallic, which is kind of interesting. But they do have those gases associated with them, and that's because they have so much gravity that those light gases are going to stick around. Yeah, very good. Now this is kind of interesting. So what you're looking at is kind of face on the early, and I'm going to change this from sun to kind of proto-sun. Proto meaning not quite the sun yet. So this would be early on in our solar nebula, not early on, kind of maybe later on. You kind of see the sun, what's going to be the sun, shining in the middle. And of course, we kind of have accretion going on in kind of lanes around the sun, but kind of a blow up of this particular planet. Can you see where this particular planet has its own disk? Okay, the Jovian, the giant gaseous planets, Jupiter, Saturn, Uranus, and Neptune, they actually have a series of moons around them. Okay, so that's kind of cool. Very cool. Okay, I'll try one more time. Okay, Okay, so a little bit ago I said that doesn't look like the sun turned on yet. We're going to talk about how stars full-fledged begin thermonuclear fusion in their cores. And I wish I could be there when ours did, although that was 4.6 billion years ago. But when they do, basically they create radiation, and associated with this radiation is what we call solar wind. And literally it's a blowing out in all directions. It's a wonderful thing. Okay, so this little animation is going to show you the time when the sun got smaller. So can you see that? One of the things that I think I would change about this animation is those yellow lines that represented the solar wind. I would keep them going because honestly, we still have a solar